Hello, in this video I'm going to run through the solutions and some of the common mistakes in version 1 of Midterm 2. Hopefully this will help you in your revision for the final exam. Okay, so the first question in this version was involving a question about volumes of revolution. So we're told to consider a solid with rotational symmetry. So that's our clue that this is a solid of revolution. And this is about the x-axis. And our solid starts at x is equal to 0 and x is equal to 1, where x is measured in meters. And if we take a slice, which we're calling this slice S, through the solid in the xy plane, with x and y being both positive, the exterior of the slice is described by the function f of x is equal to root x, and the interior by g of x is equal to x. Okay, so for the first part, we're asked to sketch these two curves that describe the interior and exterior of my solid. So first of all, set up your axes, x and y, always make sure you label those. And then let's think about, first of all, the exterior. So this is given by root x, which looks something like this. So my f of x is equal to root x. And the interior is going to be given by g of x is equal to x. So it's my g of x is equal to x. Note that they intersect at x is equal to 1 and x is equal to 0. So this shaded bit here is this slice through my solid. I'm now asked to show that the volume of this solid described above is pi over 6 meters cubed. So how do we do this? Well, the volume of our solid of revolution is going to be pi times by the integral from our start to our endpoint, so in this case 0 and 1, of my exterior, so that's my f of x squared, minus my interior squared. That's done with respect to x. So we're rotating this solid around the x-axis like this. A lot of people forgot the dx here. Remember, when we're doing an integral, we need to say what we are integrating with respect to. Okay, so the next stage is to substitute these things in. So what is f of x? F of x is root x, and we're squaring it. So we're going to have root x squared, which is just x, and then minus g of x squared. G of x is x, so g of x squared is going to be x squared again, remembering my dx on the end. So the next stage here is to actually carry out the integration. So at this point, we still have that pi out the front. We integrate with respect to x. So x goes to x squared. We increase the power by 1 and divide by the new power. So divide by 2. Same for the second part. Increase the power by 1, divide by the new power. At this point, some of the mistakes that people made were they either still had a dx here, or they forgot to put on what the bounds were. Here we have to keep these bounds here to describe this as a definite integral. Okay, so we need to state that we are evaluating this between 0 and 1. The next stage is to evaluate this. So we substitute in 1. So 1 squared and 1 cubed are just going to be 1. So we have a half minus a third. And for completeness, we should really substitute in the second one as well. This is going to be 0, but I'll include it completeness. So we have pi times by a half minus a third. A half minus a third is going to be 1 over 6. So we have pi over 6. We can bring in our units here now, meters cubed, and this is what we were asked to show in the question. So I think most people got that right. There were a few notation mistakes was one of the main problems in that question. Okay, question 2. We did a very similar problem to this. In fact, there's a very similar problem to the first one in one of the IQs. Here we are doing something similar to one of the IQ questions related to an agricultural yield. So here we're told that the yield of corn in kilograms per meter squared is given by this function here. So we have NP e to the 2 minus n minus p, where n and p are the soil concentrations of nitrogen and phosphorus respectively, and these measured in grams per meter squared. We're told what the partial derivatives of y are with respect to n and p. And we're first asked to show that the maximum yield occurs when N and P are both equal to 1. We're told that we don't need to use the second derivative test. You could if you want to. I'm not going to go through that here because you don't need to, but there are only 2 critical points here. So the reason we don't need to use the second derivative test is because if we find 2 critical points, then we substitute those critical points back into our yield function. If one of those has to be bigger than the other. So you can think of this as being like hills and valleys. Obviously, we're in 2 dimensions here rather than 1 dimension, but for simplicity, let's draw it like this. If we have 2 critical points, say here and here, this, remember, this is my function value. In this case, I'll do it in 1 dimension, f of x, and I have a critical point at x1 and a critical point at x2. Obviously, f of x1 is bigger than f of x2 here, so that is the maximum. So we just need to plug those back in and find out which is maximum. Okay, so let's start by, first of all, setting our partial derivatives equal to 0. So our critical points are when we simultaneously have y sub n is equal to 0 and y sub p is equal to 0. Okay, so we need both of these things to be true simultaneously. Okay, so let's look at our y sub n, np. It's equal to 0. Well, that implies that this bit on the right-hand side of 1 minus n p e to the 2 minus n minus p is going to equal 0. So what does that tell us? Well, this bit here is always going to be positive, so we can divide through by that. So that tells me that 1 minus n times by p is going to equal 0. Now we can consider, actually, let's just write this out a little bit further. We can set either n is equal to 1, because the stuff in the bracket has to equal 0, or p must equal 0. Okay. So now we can consider what happens if y of p is equal to 0. Now note that this system is actually symmetric, so here we're now going to have 1 minus p, n, so all the n's and p's are just swapped around. So 1 minus p times by n times by e to the 2 minus n minus p is going to equal 0. Again, this bit we can cancel out because it's positive. That tells me that 1 minus p times by n is equal to 0. And so p is equal to 1 or n is equal to 0. Now, this has given me 4 values for n and p, or 2 values for n, 2 values for p. So we have these values here. Now, what we need to do now is we need to verify which combinations we can actually have. So one of the mistakes that people make here is they go, oh, okay, well, we can have, say, n is equal to 0, p is equal to 0, we can have n is equal to 0, p is equal to 1, n is equal to 1, p is equal to 0, and both of them equal to 1. So we have 4 critical points. That's not true because these values here only tell us when one of the equations are equal to 0. So this first set tells me when my first partial is equal to 0, and the second set tells me when my second partial is equal to 0. To have a critical point, we need both of them simultaneously equal to 0. So if n is equal to 1, let's take this first one up here, then consider what happens to this second equation here. If n is equal to 1, then that means that 1 minus p must equal 0, and so 1 minus p is equal to 0 implies that p must equal 1. So if n is 1, p is equal to 1. We can't have n is equal to 1 and p is equal to 0. Now let's consider the second point. So if p is equal to 0, this one here, if p is equal to 0, then we're going to have 1 minus 0 when we substitute it into the second equation here. We're going to have 1 minus 0 times by n must equal 0. Implies that n must equal 0. So p being equal to 0 implies that n is equal to 0. So that means we have 2 critical points, 0, 0, and 1, 1. So now that we've found our critical points, we just need to substitute these values of n and p back into my original yield equation. So let's consider what happens when n and p are both equal to 0. This is just substituting all the way back into this equation here. One of the mistakes that some people made was substituting the n and p's back into these equations here, into the partial derivatives. You needed to substitute them back into the equation for yield. Okay, so let's substitute these values back into our yield function, 1, 1, and 0, 0 here. Here we're going to have 0 times by 0 times by e to the 2 minus 0 minus 0, which is just going to equal 0. Here we're going to have 1 times by 1 times by e to the 2 minus 1 minus 1, which is going to equal 1. And so we see here that this is greater than y0, 0. So our max yield occurs when NP is equal to 1, 1. So some of the mistakes that people made, they assumed that 1, 1 was automatically greater than 0, 0. That's not, you can't assume that. You have to actually substitute them back in and compare the values that come out to show that the maximum yield occurs when n and p are both equal to 1. Another mistake that a lot of people made, which was quite surprising, was a lot of people here jumped straight to doing Lagrange multipliers. So a lot of people started writing down things like grad f is equal to, or grad, let's go for grad y here. People would write grad y is equal to lambda grad g, and they would sometimes even write down g is equal to n plus p minus 1 or something like that. This there's no constraint given in this question. The Lagrange multiplier part of this comes in part B. So anyone that attempted to do Lagrange multipliers here, the question is, where is your constraint coming from? The question doesn't tell you about any constraint. The constraint only comes in part B. Here we were just looking at the critical points without any constraints. So what happens when we do have a constraint? So here we have a constraint of n plus p is equal to 1. So it's telling me that the amount of nitrogen and phosphorus I can put into the ground is limited. So we now need to work out what is the optimum concentration when this is true. Some people jump straight to saying, well, n plus p is equal to 1, so n is equal to a half and p is equal to a half. That does actually turn out to be the answer, but that's not how we calculate it. You don't know that just from this equation here. You know, you could have had, if n plus p is equal to 1, you could have had, say, n is equal to 3/4 and p is equal to 1/4. That satisfies this equation here, but we don't know if that is the optimal concentration. So some people jump straight to that point. What we should be doing is we first need to define our constraint. G of np is equal to n plus p minus 1. And subject to this constraint, the optimal concentration of n and p occurs when grad of our yield function is equal to the grad of g times by lambda for some lambda. Okay, should really write out exactly what I'm doing here, but as I'm describing it in words, I won't. This is in the full solutions though. Okay, so what is our grad y? Our grad y is equal to our vector of partials. And what is our gradient of g? And that's just equal to 1, 1. In general, this won't be true. They won't just be something as simple as this. Here I chose something nice and simple. So what do we require? So we take each of these components. So our partial with respect to n for y. I'm going to have to equal lambda times by 1, which is the partial here corresponding to g. I'm going to call this equation 1. We also need a partial with respect to p for y equal to lambda times by 1. It's my second equation. And we also have my third equation here. Call this equation 3, n plus p is equal to 1. So if we equate equations 1 and 2, we can do this because they have the same thing on the right-hand side. If they didn't have the same thing on the right-hand side, we'd have to make it that way in order to be able to equate them. So if we equate them, this gives partial y with respect to n is going to equal the partial with y with respect to p. And we already know what these are. We're given what the partials are, so we have 1 minus n times by p e to the 2 minus n minus p is equal to 1 minus p n e to the 2 minus n minus p. We can do some simplifications here because we have these exponentials will cancel on both sides. We can also expand if we want to, so we're going to have p minus np is equal to n minus np. Likewise, these np's will both cancel, so we have p is equal to n. And from equation 3, our constraint, we know that n plus p is equal to 1. So that tells me that since n and p are both equal to each other and n plus p must equal 1, n is equal to a half and p is equal to a half. And these are again in grams per meter squared, so we should include our units. Okay, so it's also nice to finish up the question by just restating what we mean by this. So we should say really the optimal concentration in the soil is n is equal to a half of a gram per meter squared, and likewise p. This question was mostly answered well. I think mainly the problems were around defining the constraint function here. Some people just didn't write down what G was. They just jumped straight to this part here. Always make sure you define what you're talking about. Okay, the final question on this version of the midterm was looking at a linear system of ODEs, which is very similar to the systems that we looked at in class, and also looked at on the problem sheets. So this model is describing a model of antagonism and mutualism. So when species are being harmful and beneficial to each other, we've got two species called x1 and x2. We have this linear system given in matrix form here, and we have a matrix describing those interactions. We're told that xi is going to be the strength of antagonistic, so negative values, or mutualistic, positive values. These are the traits expressed by species I to species j. So what this means is when x1 is greater than 0, x1 is harmful to species 2. When x1 is when x1 is greater than 0, species 1 is beneficial to species 2. When x1 is less than 0, species 1 is harmful to species 2, and vice versa for species 2. That's all it means in this case for them to be antagonistic or mutualistic. Those with a keen eye will have noticed that these are like the Romeo and Juliet models, where this is hate and this is love. So although it's been put into a biological context here of antagonism and mutualism, it's very similar to what we did before. So in the first part, we're told what the null lines are, and we're asked to determine the direction field on the null lines. So let's look at our first null line. So our first null line, when x2 is equal to x1, what do we know? When x2 is equal to x1, our equations here are coming from this matrix. So let's actually just write this out. So dx1 dt is going to equal minus x1 minus x2. So that's from this first row here. And dx2 dt is going to equal x1 minus x2. So on this line here, x2 is equal to x1. We're going to have dx2 dt is going to equal 0. So we know on this null line that we can't be moving up or down. We have to be moving left or right if we're going to orient our x1 on the horizontal axis and x2 on the vertical axis, that is. So we have to be moving left or right. So we want to see whether we are moving left or right. And that will be given by this equation here, dx1 dt, which is equal to minus x1 minus x2. We now substitute this equation here into this equation here. And we can do that either eliminating x1 or eliminating x2. It doesn't matter. The arrows will ultimately be the same. So for argument's sake, I'm going to eliminate x2 here. So dx1 dt is equal to minus x1 minus x1 plus x2 and x1 are equal to each other, so which is minus 2x1. So what does that tell me? That tells me that dx1 dt is going to be positive. This thing is going to be positive up here when x1 is negative. It has the opposite sign to whatever x1 has. So that means that we move to the right. dx1 dt is positive when x1 is negative, and we're on this null line. And dx1 dt is going to be negative if x1 is positive. So we move to the left when x1 is positive. Okay, now let's consider the other null line. So this is x2 is equal to minus x1. And on this null line, dx1 dt is going to equal 0. So we're not moving left or right. We are moving up or down. So we need to look at our equation for dx2 dt. So this is x1 minus x2. And we need to substitute this into here. Again, we can eliminate x1 or x2. In this instance, I'm going to eliminate x2 again. So if I eliminate x2 here, I'm going to have x1 minus x1. So it's going to be plus x1. So you have 2x1. So what does this tell me? Well, this tells me that dx2 dt is going to have the same sign as x1. So dx2 dt is going to be positive if x1 is positive. That means we're going to be moving up on this null line when x1 is positive. And dx2 dt is negative if x1 is negative. So we move down on this null line when x1 is negative. So now we're asked to sketch the phase plane and show our direction field on the null lines. So what does our phase plane look like? Well, let's sketch our axes first of all. So it's going to be my x2 axis. And then here, this will be my x1. We have two null lines. We're told that we have a null line x1 is equal to x2, which looks something like this. So my line x2 is equal to x1. We know on this one from the previous section that dx2 dt is equal to 0. So what does that mean? I can immediately draw on here, if dx2 dt is equal to 0, I must be moving left or right. So at this point, I'm just going to put some horizontal lines here to indicate that I'm moving left or right. We also have this null line here, which is x2 is equal to minus x1. And on that null line, dx1 dt is equal to 0. dx1 dt is equal to 0 means I can't be moving left or right. I must be moving up or down. So the arrows have to be going up or down on that null line. Okay, so what do we know? We now go back to what we learned for our direction field in part A. So let's just highlight this bit here. We're told that dx1 dt is going to be greater than 0. We're going to be moving to the right if x1 is negative. So if x1 is negative, so when is x1 negative? x1 is negative on this side of the graph, between here and here. We're on this green null line, and we're told that when x1 is negative, dx1 dt is positive, so we're moving to the right. Conversely, we're told that when x1 is positive, so that's this side of the graph, and we're stood on this green null line, dx1 dt is negative, so we move left. Now let's think about this null line here. So on the null line, x2 is equal to minus x1. dx2 dt is positive, so we move up if x1 is positive. So when is x1 positive? x1 is positive over this side of the graph. So on this null line, these arrows have to point up because x1 is positive, and so dx2 dt is positive. Conversely, dx2 dt is negative on this null line when x1 is negative. So those arrows point down. So common mistakes that people made, despite saying multiple times in class, please do not do postage stamp sized graphs, I saw things like this, or something like that with arrows drawn on whatever they might have looked like, often pointing in the wrong direction. I guess people mixing up the signs was quite a common mistake here. There were also quite a few people that drew these more as, I can only presume they're drawing them more similar to being eigendirections. They would have things where the arrows pointed along the null points. If you look back in your notes, this is the kind of picture when we have eigendirections. And you're moving along those eigendirections. That's why these arrows point along them. Whereas here with our null lines, it means that we're not moving either up or down or left or right. We're only moving in one of these directions. So when we have null lines, our arrows must either cross horizontally like this, or they have to cross vertically like this. So you shouldn't have ended up with a picture like this for your description if you're using null lines. Okay. We will be most likely doing phase planes again on the final, so practice is important. Make sure that you draw your diagrams nice and large. I'll also give a hint for the final. When it comes to drawing these things, if you're doing population sizes, and again, this will only apply if you're doing population sizes or things where we're told that we're explicitly non-negative, we don't care about what's going on in these three quadrants here. If this is, say, if this was predator and prey population sizes, we don't have to draw all of these other things here. You just have to draw what's going on in the positive quadrant. In the case where we're dealing with population sizes. Also, if you've, say, got null lines crossing, don't draw everything going on down in this corner like this. It's very difficult to then subsequently draw what's going on, especially, say, if you have another null line going over there and you're trying to draw your arrows on here, you've got all of this space here. Okay, make sure that if you've got something like intersections going along, make sure you draw it nice and big so you can actually see what's going on. Okay, the next part of this question, we're asked to consider the trace and the determinant of A, and then figure out whether our origin is stable, unstable, and whether it's a node, a spiral, or a saddle. So remember our matrix A here is -1, -1, 1, -1. Our trace, which I'll call tau, is equal to -1, -1, which is -2. Obviously, this is negative. Our determinant, I'll call delta, is equal to -1 times by -1 minus 1 times by -1. So that's 1 plus 1, which is 2, which is positive. Okay, so let's at this point go all the way back to the formula sheet. So what are we told? We have a negative trace. So that means that we are over on this side of our graph, of this diagram, and we have a positive determinant. So that means that we are in this quadrant here. So we don't know at this point whether we have a stable node or a stable spiral. So at this point, we need to look at our trace squared minus 4 times our determinant. And that will tell us whether we are above or below that curve. So tau squared minus 4 delta, in this case, is going to be, we have -2 squared minus 4 times by 2, which is 4 minus 8. It's -4, and so this is negative. So that means if I go all the way again back up to diagram at the start, we have a negative trace, positive determinant, and tau squared minus 4 delta is negative, which means we're above this curve here. So that means that we have a stable spiral. So a common mistake is that people put a stable node instead. So 0, 0 is a stable spiral. I think most people managed to get this correct. So this bit here indicates that we have complex eigenvalues. And when you have complex eigenvalues, it means you have some sort of oscillation. Okay, the final part, which was probably the hardest question on the paper, or at least the thing that people struggle the most with. We're told that we initially have some values for x1 and x2, and we're asked to describe the relationship between these two species, how it changes in the short term and in the long term. So if both of these values, I'm going to describe it in words up here rather than write it all out. There's obviously the solutions. We're told initially that, let's pick a color that we've not used yet. Let's go for gray. Okay, so we have initial values of x1 and x2 being positive. So suppose we start off somewhere over here. Okay, x1 and x2 are initially positive. What happens? Well, we can think about movement through this phase plane. We can think about a trajectory. So first of all, I'm going to draw a trajectory. So what's going on here? I know I'm moving left, and I'm also moving up. So I'm moving up and left, but I also know that I'm crossing this green null line horizontally. Okay, so that bit there, I should be crossing it horizontally, going to the left. Okay, and then I keep going in this direction. So start that again. So we're moving up and to the left, cross that null line going left. Now I'm moving down and to the left. Keep moving down and to the left until I cross this null line vertically going down. Not the best of sketches here. And then I keep moving down, but now I'm moving down and to the right until I cross this green null line here, and I cross it horizontally, moving to the right. Keep moving up and right now, and then I cross this null line, moving vertically up. Now I'm moving up and to the left again, just as I was to start with, until I cross that null line, moving left, and then so on, until we spiral in eventually. Okay, so our trajectory would look something like this. So what does that mean? Well, x1, x2 being positive means that they are mutualistic. So in this region, x1, x2 positive means that both are mutualistic. This region that they go into next, over here, we have x1 is negative and x2 is positive. So I'm going to abbreviate here. x1 is going to be antagonistic and x2 is going to be mutualistic. They then move down to this bottom left quadrant where both are negative. So both are going to be antagonistic. And then they move finally into this bottom right quadrant where x1 is positive and x2 is negative. So x1 is going to be mutualistic and x2 is going to be antagonistic. So both species start off being mutualistic, then x1 becomes antagonistic, then x2 also becomes antagonistic, then x1 becomes mutualistic, x2 becomes mutualistic as well, and then the cycle continues. But as this cycle continues of going between antagonism and mutualism, with antagonism, or with species one leading species two, so species one changes and then species two essentially copies species one. These cycles between antagonism and mutualism get smaller and smaller. So remember in the question it said that the values of x1 and x2 describe the strength of antagonism and mutualism. The smaller these values are, the less antagonistic or mutualistic they are. So a large value over here of say x1 indicates strong mutualism. A value down here indicates quite weak mutualism. So these cycles are getting smaller and smaller, these oscillations and fluctuations between antagonism and mutualism, they get smaller and smaller in the short term. And then in the long term, because we have a stable spiral, the point 0, 0 is stable. So in the long term, both species tend towards having trait values of 0, which means that they're neither antagonistic nor mutualistic. Okay, so that was the main part of answering part D here. Again, I'm not going to write this out just because I've described it in words, and there's quite a lengthy description of this in the solutions. People really struggled with this, describing what was going on. Saw quite a wide range of incorrect answers here, from talking about these as population sizes to saying that they grow when clearly they're shrinking. They're going down towards or rather the trait values are shrinking. They're going down towards 0, 0. Sort of some insufficient descriptions like they cycle, which is a partial answer. But we want to know more about this. We can describe more about this based on what we know. We know, that species 1 leads species 2 here. Species 2 follows species 1's antagonistic or mutualistic traits. We know that those spirals decay because it's a stable spiral. So in the short term, we're getting swings between antagonism and mutualism, but over time, those oscillations get smaller and smaller. And then eventually they die out completely, with neither species being antagonistic or mutualistic. The interpretation is definitely something that lots of people struggle with. The best advice I can give is essentially say what you see. So in this case, I drew on a trajectory and then just described what happened as I moved through these different quadrants here. So I'm just describing what is happening as I'm essentially walking along this trajectory here. That's all I did in terms of describing the behavior in the short term. So short term is essentially all of this stuff here, all of this stuff. The long term is what is going on as t tends towards infinity. So what is this point here? It happens to be stable, so that means that the species is going to stay there stably. If it was unstable, then we would be spiraling out, and you would say, in the long term, they become wildly more and more antagonistic and mutualistic if it had been an unstable spiral. If this had been, say, a center, then you would have said in the long term, they stay on their trajectories, they keep going in ellipses around being antagonistic or mutualistic forever. Okay, that's it for this summary video. I hope that was helpful in your revision ahead of the final.